Hey folks, welcome back to Spreadsheeting. Today we're going to start getting a little bit more complex and a little bit more serious with some of the stuff we're doing. So in game design, there's an interesting problem where, when you're making a game and you're balancing a game, if you're making resources and you want to know how much you should be giving the player. Let's say that they're mining some ore that they found. How much ore should you give the player? And how do you know that you're right? I think one of the hardest things to start answering as a new game designer is, and even a season one, is like, where do you start with that question? Um, so I'm going to show you some methodologies to start kind of figuring that out yourself and learning what's right, a tool set for you to begin building game systems and economies. Um, where we're going to start today and we'll build towards is something that I'm going to call an MCMC sim, which is a Monte Carlo Markov chain simulation. That's a lot. Don't worry about it right now. We'll get into that when it starts to make sense. But today we're going to start talking about randomization in game design. So randomization can appear in a lot of different ways. Um, you know, the easiest one is crit chance. That's something that you see all the time in video games. You see like 2% crit chance where you double your damage. And so percentage chances are a pretty basic and easy way to work with probability and randomization. Randomization is great in video game design because there's a part of our brain that's just wired to feel excited when you get something that's rare. A chance to happens feels very good for us, and this is taken advantage of often in casino gaming. But in video games, it's still a powerful mechanism that you can use in a positive way to reinforce behavior and to really help also make players feel a sense of progression. So with that in mind, let's jump into the spreadsheets, and I'm going to start talking about a couple different types of probability and randomization and ways that you can work with them. So let's head on over there. Your spreadsheet should look something like this. If you haven't followed along so far, highly recommend you go back. Otherwise, you could start kind of somewhere similar and just follow us along this way. So when we talk about I'm just going to noodle for a second, actually. I'm just going to noodle. We'll delete it in a moment. So let's say that, um, you know, you have a, let's follow that damage model. Let's say that you have a 2% chance to crit. So we're going to say that your base damage, and this is just some other game. This is not our game that we've been making. Base damage is 10. Your crit multiplier. So when you crit, it's going to multiply your base damage by 2. You're going to double that damage. And your crit chance don't need to type is, um, it's also 2%, but we're going to put 0.2 in here because we're working we're going to work with random normals. And so percentage 0.2, and we're going to format that as a percent. So there you go. That's 0.02. Sorry, that's what I now it's being goopy. There we go. 2% crit chance. So if in this column we did just a random function, random normal, and we drag this down here, some number of rows, you could go for as long as you want to. And then we'd say like, random chance damage is, I'm going to show you another function here, an if function. So this is just like programming, and if you scripted or programmed, it's quite similar. So we're going to say if the roll is 2% or less, it's a crit. If it's not, otherwise it's not. So let's do this. If, nice little kind of description here. So we put a logical expression in, and if it's true, and then if it's false. So the expression is going to be if this value here, if this random is going to be less than or equal to our crit chance, and you're going to lock that in with an F4, then we get a crit, and I'm going to just put true in there. Otherwise, actually, you know what? We're gonna do it a little different. We're gonna just say we're gonna put the damage in there. That's what I meant to do. So if it's a crit, we're going to do this times this. We're going to lock those in, and then if it's not, it's just going to be this damage. So let's hit enter and fill that down. So there you can see the crit happen there. Doesn't happen very often, does it? If we start to play, like what if we make this 5% crit chance? You can start to see it pop up a little bit more. So what you're saying is about 5% of the time that you attack, so every time you simulate an attack here, you're getting a crit. So this is probably one of the most common, or if not the most common form of probability. This is the best form for you to display to a player for the most part because it's easy to understand. Everybody understands sort of the proportion of 5% and what that means. But there are other ways of working with probability, and that's what we're going to start to get into today. I think one of the most important ones and best forms of probability is weighted distributions. So what a weighted distribution is it's effectively a card deck. So if you can imagine you have a deck of cards and you have 4 of each suit in that deck, right? You shuffle it up. That means that every time you draw a card with a suit, so if you've got four, yeah, so 4 clubs, 4 spades, 4 diamonds, 4 hearts. That's your deck. Let's not worry about the numbers right now. All of that. That's the deck you make up. If you draw a diamond, what you're saying is there are 4 of those cards in the deck, and your chance is equally stacked against all of the other cards because there's 4 of them in that deck. That is weighting. But if you put 2 diamonds in, 2 spades, 4 clubs, and 4 hearts, all of a sudden the odds are stacked a little bit differently, right? The weights are different. And so we're gonna start working with a weighting model similar to a deck of cards. So let's jump in there. So what we're gonna say is let's go the fantasy that we're gonna make is exactly what we said before. It's mining. So we're gonna start mining a resource. So let's go right here. I'm gonna say this is gonna be I'm gonna just combine these columns here, merge cells up here. We're gonna call this a mining simulation. No, not mining simulation. Mining weights. There we go. We're going to work into the mining simulation. And I'm going to give that a brighter header. And then we're going to pick one of these guys. And I'm going to copy this and put it down here. And I'm going to color this whole row a light green. Great. And then we're going to start playing around with weighting. So the first thing we want to do is say that every time, so what we're going to do is say every time the player strikes the rock, strikes the ore node, they're going to get some amount of ore out of this. And we're going to start by kind of saying how many possible amounts could they get. So I'm going to create a bunch of amounts. I'm going to say 10, 8, 6, 3, 2, and 1. And those don't need to be floats. They can just be integers there, like that. Great. And so when you look at this, what you probably would think as a player and as a designer is that more likely you'll want them to get these sort of 3, 2, and 1s most frequently. But 10 feels pretty good. 10 and 8 especially feel pretty good, and 6 is all right. And so you'll want to come up with some sort of a weighted distribution that means that sometimes, very rarely, 10 happens. So when it does, it feels very good. But pretty frequently, the lower numbers happen. And so what we're going to do is just in this next section, I'm gonna move all of this down. So grab this with me. We're gonna create some headers here. So let's just grab these. So if you highlight these cells and you click on the edge where the hand is and drag them all down one, we're gonna create some headers here. So the first header is amount. This is the amount you get when you strike the node. And then we're going to create weight in the next column. And so we're just going to put numbers in here. Think of these numbers like the number of cards that would be in a deck. Let's say that you had a deck of cards with these numbers printed on them. So 10. So when you drew the card that had 10 on it, you would get 10 ore. And that's the game that you're making. So we're going to only put one card in this deck of 10. I'm going to put 2 of 8. I'm going to put 5 of 6. Let's put 10 of 3, 20 of 2, and 30 of 1. So, when you look at this, you can tell like with 30 cards of 1, you're going to draw that pretty often. So every time you draw cards, 1 is going to come up pretty frequently. The other thing that's important about the way that we're making this weighted distribution is that we're going to make the assumption that every time you draw a card, you shuffle it up again, the whole deck, and then you draw again. So that means that because there is a different type of distribution where you could say that every time you drew a card, you took one off, so this will become 29. And that means that the weight of everything else increases. And that's actually a really cool method of probability for when you want something to have, maybe be very rare to begin with, but have an increased chance over time. And there's some really interesting systems you can build around that. But let's not dive too far into that yet. Let's stick with what we have. So we're going to assume that every time you draw a card, you draw one, great, you get 1 ore, and then you shuffle the whole deck up again. That's what we're going to do. Okay, so the next thing is at the bottom here. I'm gonna actually do a sum and get the whole weight. What is the total of all of this? It's 68. And I'm gonna make this a different color. Because it's calculated, I'm gonna make it yellow. This is what I like to do. Great. So 68 is our total weight. So that's how many cards are in the deck. So the next column, I'm actually going to calculate the probability chance of you getting one of these cards. So how we're going to do that is we're going to do this number, and we're going to lock in the column, but nothing else, divided by this number. We're going to lock that in. And wants to suggest to fill it all down. Great. Then I'm going to highlight all of this. So those are lots of decimals and format as a percent. Awesome. And because this is calculated, I'll make it yellow. Cool. So drawing the 10 card right now is about a 1.5% chance. Pretty low. But there's about a 44% chance of getting the 1, which is pretty high. And you can see that cumulatively, all of these add up to 100%, basically. And, that's 68 divided by 68, of course. But if we go sum of all of these, oops, this should also add up to 100%. And it does. That's great. So you know that in a 100% chance, you have a 100% chance of getting one of these cards, basically. And you can see what their distribution is. And if you play with these numbers, you can start to see the distributions change. And what's interesting is that if you increase one number, so let's say I put 40 of these in, all of a sudden you can see all of the weights shift because you've changed that one number. So weighting is a proportional way of doing probability, and it's probably one of the most useful ways of doing probability in games. So next, we're going to start simulating this. So what we want to do is I'm going to start by making a mining simulation sheet. And what we want to do is get a random weight. So we want to roll the dice, or we want to draw a card effectively and see what that weight is. But there's a couple of things we have to do to get there first. Whoops. All right. So the next thing we're going to need to do is get the cumulative weight. So let's talk about this for a moment. So what we're going to be doing is rolling a number between the minimum and the maximum of the weights. And so these weights, like that number, if we rolled between 1 and 68, they have to kind of like go sequentially in order. And so we have to get the weights cumulatively in order to appropriately get that number. Now that's a lot. So just let's start doing this, and it might start to make sense in a moment. So what I'm going to actually do is do the sum of this and this. Whoops. So I'm going to do B30 to B30, and I'm going to lock the first one in, but not the second one. And there's an important reason we're going to do this. So if I drag this down one, all of a sudden you're going to see 3. So what it's doing, so this is now between B30 and it's summing all of these. And so what we're doing is kind of stacking these values on top of each other. So we're going 1, 2, 3. The next increments, we're stacking these cards. 4, 5, 6, 7, 8 is going to be the next one. Whoops. Yeah, there we go. So I'm gonna just drag these down. And why this is important is because if we're getting a value between 1 and 68, and I roll like 2 or 3, that means that proportionally I would have to get this value if I got a 2 or a 3, because that's what it lines with. Whereas if I got 4, 5, 6, 7, 8, I would actually get this. So we have to generate the values cumulatively in order to get the right number. So let's play with that. Let's see what happens. Let's start seeing what happens. So I'm gonna first off get a random value between 1 and 68. Now I'm gonna do this a little bit differently. So last time we did rand between. I'm not gonna do that this time. I'm gonna just do a random normal. So I'm gonna go equals rand, and it's gonna generate this number. Then I'm gonna multiply that in here by the total weight potential. I'm going to lock that in. And we don't need all those decimals, so I'm just going to move it over. Great. So we've got a random weight. And then we're going to get a random amount. Actually, so then we're gonna say, so if we roll 3 here, or if that's the amount that we get, and if I hit delete, you'll see lots of random numbers pop up here. Awesome. So we'll say, like, what is the actual weight? Let's get the actual weight. And normally I wouldn't do this. This is just for demonstration to show you guys and good practice here. So let's get the actual weight. So what we want to say is if I rolled, let's say, a 68, well, 66, I would get a 1. That's what I'd be getting. So I'm going to try to just find this weight here based off what I rolled. And so what we're going to do is this. We're going to do an index match, but we're going to do kind of a special match. And it only works when it's inside of another function. So if you can only do it inside of something like index. So let's do this together. So we're going to do an equals index, and really what we want to do is look up the weight that we got. I'm going to lock that in with an F4 colon, and then what I'm going to do is put in a match. We're going to do something kind of interesting. So what we're going to do is say we're going to put a formula in here. So we're going to say actually, so we're going to say returns true. And this only works inside of this formula. So if it returns true, if this, I'm going to lock in that column, is less than or equal to a value in the cumulative weight, I'm going to lock that in and put 0, close that up. So the actual weight we're getting is 30 based on that roll. I'm going to click in an empty cell and hit delete. So what this is saying is this is the actual weighted number that we're getting. Now let's get the amount, random amount, and we're going to do the same thing. So let's just follow along same formula. So we're going to look in this time we want to look up the amount that we get. I'll lock that in at 4 colon space, and we're going to put it in match. We're going to match true under the circumstances of this weight, and lock in the column. So push F4 3 times. It's less than or equal to the cumulative weight, and lock that in. What we're saying is return the position of the value that is less than or equal to the weight that returns true as less than or equal to the number that we rolled randomly between 1 and 68. And so let's do that. Enters, great. So, oops. Did that work? Did I do it right? Oh, and I forgot I have to put a 0 at the end there. If you don't do that, that might break. So remember that 0, 1, and -1 are integers that you can put into the end of a match function to say what kind of match it is. 0 is closest match, I believe. Okay, so now we can just drag this down, all 1,000 rows, all 3 of those things together, and simulate mining. Gonna get there, promise. Let's do it. All the way down, there we go. Boom. Okay, that is awesome. And so what we can now do is kind of do some analysis like we did last time. So what I'm going to do is sort, and I'm going to put unique numbers from the amounts in here from C2 to C. Great. So now we see all the values that would typically come up, and let's count how many times they happened. Sorry, count if, and you remember last time, so we'll put the range in the criteria, so we'll go C2 to C again, and the criteria is if it's that, and I'm going to lock in the C2 to C range as well, and fill this down. Great, so we can see in 1,000 rolls how many of each happened, and let's do this. Let's sum that. Sorry, 999 rolls. And then what we're going to do is actually I'm going to move all of this down just one. Let's do amount probability. And so let's take a look at in this simulation what the probability of drawing one of these things was. statistically speaking. So what I'm going to do is do this number equals this divided by this number, the total. And I'm going to lock that in so it doesn't change and fill that down. And this should look fairly similar. So 1.8 for a 10 to this. Now it's a little bit different. And the reason why it's a little bit different is because we only did 999 simulations. What this is saying is in a perfect world, under infinite simulations, this is the probability chance you'd get. So the fact that these are really close is great. It means that it's true, but there's a little bit of variance because it's random. We're playing with randomization, and it's not infinite simulation. So it's almost 1,000 simulations, and that's it. So um, so cool. So we're seeing that. Now I'm going to show you one more useful thing, I think, for doing these kinds of of things. And I'm going to calculate here. So I'm going to calculated the average mind. There we go. Um, and so this is a really helpful one for me sometimes when I look at these things. So what this is basically like it means that if I looked at infinite simulations of all of my um, all of my mines, basically every time I mined ore, every time I drew a card, and I looked at the total of the amount that I was that was there, basically that I had mined. Um, roughly how much per mine was contributed if it was all divided amongst all of these? Roughly how much was mined from each strike kind of each of these sort of distributions. And so there's an easy way to kind of do that. And you might not know what I mean right away, but take a look at this. So if I did this and I multiplied the amount, lock in the column, by the probability, lock in the column, and hit enter, it's given us a number. And I'm gonna just put this down to like 2 decimal places for now. It's a little bit easier to look at. And I'm gonna drag that down. Great. So what this is saying is really kind of the best like for its value, for its money is this 2 with a weight of 20, because I'm getting roughly 0.59 contributed to my infinite supply of simulations. 0.59 is each strike is kind of coming from that. And if we add these together, this should be basically the average amount that I'm getting from these weights. Basically 2.29 should be the average amount. If I go back to my mining simulation and I get an average here, it may not look like that because we're not doing infinite simulations. Well, it's 2, so pretty close. Maybe if I gave that 2.17, there we go. So this is saying basically on average, what over infinite, draws, you'll be getting about 2.29. And this is how much on average is being contributed from each of these mines. And so you can see that the value of 2 is quite high. If you wanted to like even these out or something, you could do that. You could try to take that approach, or you could say like, no, I like that mostly you'll get 2, and that's the average. My dog's going crazy in the background. Sorry if you hear her. That you'll be getting from there. So, anyways, this is weighted probability, and it's a very important way of doing probability in games. Think of it like a deck of cards. Or another way to think of it is a bag of marbles, colored marbles, or a lottery. There are a number of different analogies for how this works. Deck of cards works best in my mind. So think of it that way. There's a lot of ways that you can apply this to game design in general. I think it's one of the more powerful ways of using probability. It's a little bit less user-friendly, user-facing, so it works really well for things in behind the scenes where you don't have to tell the player like you have a 10% chance of getting this many ore. Um, but it just feels good when you get more infrequently. Um, so next, we're going to start looking at building a weather system. So part of our Monte Carlo simulation, what we're going to say is there's going to be a random weather system, and it's going to be sunny, rainy, cloudy, and on different days, there's going to be different types of vegetation that grow depending on what the weather system is that day. And it's going to be a random amount each day, but it's going to be dependent randomly upon the weather. And so that's going to be the inception of our Monte Carlo Markov chain simulation, and I'll explain a little bit more what that is and why that's a helpful tool for you in game design. Anyways, if you have any questions, please feel free to leave comments below, reach out, use, check out the link to see the document that we just built together, the Google Sheet. Good luck, and I hope this was helpful. Thank you.